All right, so before we even look at this paragraph here, let me move off to the side and give you a quick example of what I mean by average rate of change. So let's say I'm going on a trip. Okay, what would be a good place to go? Not up north, right? Because of all that flooding. Say I'm going where? Oh, somewhere I can drive to. Somewhere I can drive to. Oh, let's not go to Houston. Let's go. Let's say I'm going to San Antonio. They're dry in San Antonio for the most part. All right, so at time, and this is going to be my t-axis. That's what stands for time in hours. And up here we'll have miles. That'll be my y-axis, miles driven. Now suppose at time t is equal to 0 hours, I've driven 0 miles. So 0, that's going to be my first point, my origin. After 1 hour, let's say I've gone about 60 miles. After 2 hours, I've gone 120 miles. After 1 hour, I'm at 60 miles. After 2 hours, 120 miles. And I'm going to connect this with, right now, just a straight line. As straight a line as I can get out of this. Might have to move this point a little bit. Make it a little bit bigger. And of course, I'm going to keep driving. So far, so good. Any questions up to this point? Okay, so then I pose the question, what is my average speed for the first 2 hours of this trip, over the first 2 hours? Over the first 2 hours. So the wording is important. So I want to know, over the first 2 hours, what is my average speed? That's correct. But let's see why. So what is my average speed over the first 2 hours? The reason why I pose the question like this, over the first 2 hours, I'm trying to imply some type of interval. Okay, so starting from 0, going all the way to 2. Is that clear? Okay. So my average speed to calculate the average speed, I just have to take the distance that I've gone. So to represent the distance that I've traveled, we're going to use this. It looks like a triangle. This is the change in y. The change in y divided by the change in time. Basically, how far I went and how long it took me to get there. How far I went divided by how long it took me to get there, to be more precise. Okay. Now these are coordinates in the Cartesian coordinate plane. We can represent them using ordered pairs. For example, this coordinate down here, that's just 0, 0. And since we're doing this over the 2 hours, let's skip up ahead to this one. What would this coordinate be?
2 and 120.
2 and 120. Now this behaves like T1. This is Y1. So I'm saying that this 0 is my T1. This 0 is my Y1. This is my T2. This is my Y2. All right, so the change in Y, to find the change in Y, we just have to take the difference of Y2 minus Y1. Let me make sure I'm still broadcasting here. So Y2 minus Y1 and T2 minus T1 on the bottom. All right, so for those of you that are coming in that went to go print out the notes, we're taking a trip. Okay, I'm taking a trip, not you guys. I can't fit you guys all in my truck. Traveling somewhere. I think we said San Antonio, and T represents the time in hours. The y-axis represents the miles that I've driven. So at 0 hours, I've gone a distance of 0. After 1 hour, I've driven 60 miles. After 2 hours, I've driven 120 miles. And we posed the question, what is my average speed over the first 2 hours? And emphasis on over the first 2 hours to imply that there's some type of interval there. Now, the average speed is just the change in the distance divided by the change in the time. The change in the distance, y2, is 120 miles. What's y1? 0. T2 minus 0. 120 divided by 2 is 60. So 60 miles per 1 hour, or just per hour. The 1 would be implied. So 60 miles per hour. This is my average speed, my average velocity. Okay, any questions here over the concept of average speed? Now, like I said at the beginning, we're looking at average rate of change and instantaneous rate of change. I've given you an example of average rate of change. For instantaneous rate of change, the questions will be posed as, what is the instantaneous speed, or what is the speed at t is equal to 2 or t is equal to 3? There will be no interval actually specified. That is the difference between the two. For this average rate of speed, average speed, we did it over the interval from 0 to 2. But for instantaneous speed, you could see a question like t is equal to 2, t is equal to 3, t is equal to 1, and give me the instantaneous speed. Okay, and we'll get to instantaneous speed a little bit further down here. But for right now, this is average speed, and I've hopefully given you an idea of the difference between average speed and instantaneous speed. Now, are there any questions? Any questions at all? So we're going to look at some more examples. This is just to start us off. I'm going to check this periodically just to make sure that I'm still broadcasting that thing. Okay. Because if it messes up, then I might need to reconnect it. All right, so in the late 16th century, Galileo discovered that a solid object dropped from rest, not moving near the surface of the Earth. So all that means is like from right here, like if I was to drop it, not from orbit. Near the surface of the Earth and allowed to fall freely, will fall a distance proportional to the square of the time it has been following. Proportional implies that there's some type of constant involved here. So if we were to write this out, and I wouldn't expect you to be able to write this out on your own, that's why I'm going to give it to you. We're going to represent this as a function of t, function of time. F of t is equal to, where it says distance proportional, the constant that we'll use is 16. Now it's 16 because this equation is valid for when we're working with feet. So this is in terms of feet. And it says proportional to the square of the time it has been falling. How do you think you would represent that mathematically? The square of the time that it's been falling.
The time is t, and square, I guess t squared.
There you go, t squared. 16 t squared. This is how we would represent it. Now this is in terms of feet. If we're looking at meters, this equation will change slightly. The constant will change. It'll be f of t is equal to 4.9. So this is in meters, m per meters. 4.9 t squared. Okay, so I specify it because, well, for this first example, they don't really tell you if you're talking about feet or meters. But for this example down here, they do. 450 meters above the ground. Okay, so just FYI. So let me go back up here. All right, so the reason why we're going over this is because you'll need this information for the next few examples. Bless you. Okay, read example 1. Let me take a look at how to approach it. Okay, so a rock breaks loose from the top of a tall cliff. What is its average speed? A, during the first 2 seconds of fall, and B, during the 1 second interval between second 1 and second 2. So I think for this, it would help if we had a graph. So this is where I'm going to bring Mathematica into play and show you guys how to make a graph out of this. The function that we're going to be using is going to be the one up here. F of t is equal to 16t squared. Now in Mathematica, let's see, have any of you all received the email yet? Just curious. Not yet? That's all right. No? Okay. Maybe it's taking some time to go through. You got the email? Okay, good. Yeah, you'd have to create an account. So this is meant for you to do from a laptop where you actually want this software on, okay? Mathematica should be on some of the lab computers already that are here on campus. But this is for you at home. So you can have it. As soon as they told me I could have it at home, I was like, down. Okay, so let's move over here to Mathematica. I already have it open. I was playing with it the other day. Okay, so for this example, if I want to plot, make a graph or plot it, maybe I should close this and just start from scratch. Let's see. Make a new notebook. So the command that we're looking for here is plot. How we're going to create our graph. Now, if you, and this is where Mathematica is pretty powerful. you usually have to give a command and then you have to give arguments. Even I sometimes forget what the arguments need to be. But if you ever forget what the arguments need to be, if you type out at least a little bit of it, you see here plot, there's a little I next to it. If you click it, it'll bring up what the command should look like and it gives you examples. So plot, F means you define some type of function, and then in curly braces you have to define an interval. So let me go down to the example so you can see. So after plot, you put a bracket, you define the function, and then in curly braces, you're going to define an interval. So sine of x, and then a comma, curly brace, and then since your variable is x, your variable needs to be x inside the curly braces, and you define an interval from 0 to 6 pi for this one. For ours, since we're only doing it over the first 2 seconds, maybe we'll go from 0 to 3. That would be probably appropriate. But our variable is going to be t. So let's input that. All right, so plot, and then I'm going to put a bracket. You don't have to input it as f of t is equal to 16t squared. It's already going to assume that it's a function. You just need to put in 16t squared. And then you need to put a comma, a curly brace, and then you need to specify the interval. Our variable here is t, so I need to specify t. Where I want to start at, I want to start at 0, and I want to end at 3. So do we want to do 3? No, let's go ahead and keep it at 2, just so it's consistent with my notes. All right, so 2. So I close the curly braces, but then I also have to close the outer bracket. Now with Mathematica, to actually get the output, and I always mess this up sometimes. I think it's Control Enter, but it's actually Shift Enter. So when you want the output, you have to hold down Shift, and you have to hit Enter, and then it'll spit out the graph. So this is our, okay. And it's nice because then I can copy it over here to example 1. Oh, not like that though. Yeah, so OneNote's kind of funny. I have to paste it as an image. I can't just control V it. There we go. And there's our picture. So at 0, it's at 0. At 1, it's at 16. At 2, it's at 64, just like it should be. And let me copy this, because I'm going to need it for the next example. I need 2 copies of this. So this is time. This is feet. This is my y-axis, but it's in terms of feet. Now the original problem, it asks, well, it states, a rock breaks loose from the top of a cliff. What is the average speed for part A during the first 2 seconds of fall? During the first 2 seconds of fall. So when you hear that wording, during the first 2 seconds of it falling, it sounds like they're specifying an interval over the first 2 seconds, so from 0 to 2. Now I'm going to do this in a dark red, or in a red, just in general. Over that interval. We know that this is the origin, and that's 0, 0. Up here at 2, If you don't know what that is, remember the function is specified. You can always substitute in 2 into the equation and get back what the y value should be, or the function value. Two and 64. What I mean by that is the function that we're using is f of t is equal to 16t squared. If I want to know the value of the function at 2, I just have to substitute into it. So f of 2 is equal to 16 times 2 to the second power, so 16 times 4, which is equal to 64. That's where the 64 is coming from. Is that clear? Okay. So this interval that we're looking at, it's t from, see, the best way to do this would just be like this. T from 0 to 2. That's the interval that we're looking at. Now, you're familiar already with this notation, the change in t. Right? I introduced that earlier. It just means t2 minus t1. In other words, it's the length of the interval. From just looking at the graph, you should be able to tell me what the length of the interval is since it's starting at 0. What's the length of this interval? I'm sorry, of the interval on the bottom. 2. 2 units. Bless you. 2 units. Now, what I'm going to do is I'm going to introduce a new notation for this. Okay. This change in t will still be valid, but sometimes it is presented as h. Okay. They mean the same thing. It's just the length of the interval. That's all that it is. The length of the interval. Is that clear, guys? So now I might introduce an h here, or you might still see this change in t notation, but they mean the same thing. Just know that. Okay, so we still need to find the average speed. So yeah, I've been taking it really slow, trying to make sure that everything is clear here. But are there any questions up to this point? Anything that's not clear? Anything that you think needs further clarification? No? Okay, so we've done one of these problems already. How do I go about finding the average speed over the first 2 hours? Well, let's see. So the average speed is equal to the change in y divided by h. I could put the other notation to change in t, but I want to get you used to seeing h. Now, for the change in y, that's y2 minus y1 divided by the length of the interval here on the t-axis. And we've already discussed what the length of this interval is. We know that that length is 2 units. All right, so 64 minus 0 divided by 2. So 64 divided by 2. 32 feet. And in this case, t is in terms of seconds. So it's 32 feet per second. 32 feet per second. Okay, I'm going to give you about 5 minutes, and I want you to do part B. So I went in depth for part A, but there's still a part B here. So a rock breaks loose from the top of a tall cliff. What is its average speed for part B during the 1 second interval between second 1 and second 2? So they're very, very specific about the interval there. Take a few minutes and work on that. And then we'll take a look together. Okay, just to gauge where you guys are. How many of you think you're done? Okay, keep on.
So it's
And so I'm going to copy this graph off to the side. And let's take a look at what it's asking for in this case. Okay, so let me ask you, what is the function that models this graph right here? I gave it to you at the beginning. 16t squared. F of t is equal to 16t squared. So if I want to know the value of the function at any value of t, all I have to do is take that value of t and I just have to substitute it into that function, that equation up there. And it'll spit it out for us. Now for this problem, they were asking over the interval from 1 second to 2 seconds. So that's this interval here. Right? Now just looking at it, so it really helps to have the graph. We're not always going to have the graph. But in this case, we do have the graph, and you can just eyeball the interval. What is the length of this interval? 1 unit. 1 unit. Now we do need the coordinates here. At t is equal to 1, what's the y value? So what's the y coordinate? If I substitute 1 into here, I get back 16. Good. And we already did it for 2. It's 2, 16, 4. So our delta t, or change in t, is the same as h, which in this case is 1. Now what if you don't have the graph? And I did the example at the beginning of class. Remember that the change in t is just t2 minus t1. You just have to take 2 minus 1, and that gives you 1. But that's just the length of the interval, okay? All right, what's next? Okay, so the average speed. Is the change in y divided by the change in t. So the change in the distance, 64 minus 16, all divided by 1. The change in t is the same as h, and that we've already established that's just 1. 64 minus 16, what does that give us? 48. We don't have to divide it by, we divide it by 1 technically, but that's it. This is 48 feet per second. All right, so how many of you were able to get that? Good. For those of you that didn't, do you have any questions? Or do you see where you went wrong at? Yeah? Okay, so up to this point, we've only talked about average speed. Now let's look at instantaneous speed. Unless there are any questions. Are there any questions before we move on? I want to give you guys one last chance here. One last chance. If you have a question after class, of course, you can ask also. Find the speed of the falling rock in example 1 at t is equal to 1 and t is equal to 2. So they're very specific about t this time. They're not giving you an interval. They're telling you what's the speed when t is equal to 1, and then what's the speed when t is equal to 2. This implies instantaneous speed. So when you're given an interval, like we were in the previous example, that's how you know you're talking about average speed, average rate of change. In this case, it's instantaneous speed, instantaneous rate of change. So let's do the first part together. T is equal to 1. And I have my graph over here off to the side. Let's move off to the side and let's take a look. Well, I can fill this in. For part B, the answer was 48 feet per second. Oops. Okay, so yeah, so let's go down here to this graph. And we're interested in the speed at t is equal to 1. So we're looking at t is equal to 1. I know that the function is f of t is equal to 16 times t to the second power. Everything that's been established already. Nothing too new here. So let's look at why what we were doing previously doesn't exactly work here right off the bat. So you know average speed is the change in y divided by the change in t, but change in t is the same as h, which is just the length of the interval. Correct? If they're telling us find the speed at t is equal to 1, I mark this point. Well, what's that interval? What's the length of that interval? 0. Very good. The length of that interval is 0. So it doesn't matter what the top is. If I do this, you see the problem. What's the problem? It does not equal 0. Be careful. It is undefined. Undefined. So that's why this won't work, because the answer would be undefined. So instead, what we're going to do is we'll create our own interval, and we'll see what happens as that interval gets smaller and smaller and smaller and smaller. Okay, so let me erase this. Any questions over that? So hopefully you understand now why, how instantaneous speed is different from average speed a little bit better. So let's start by specifying our own interval. And let's go with what we know for right now. What is the length of this interval? It's 1 unit. In fact, this looks very, very familiar, right? This is basically what we just did in the previous previous part B. This is 116. This is 264. I'm not going to make you go through the entire computation again. You've already done it. You know that the average speed, or the speed, let's just put speed in general, change in y divided by the change in t, is 64 minus 16 divided by 1, which is 48 per second. No surprise there. But like I said, what we're going to do is we're going to shorten this interval. We're going to make it smaller and smaller and smaller. So what we'll do next is let's do it again, but let's make our interval from 1.0 to 1.5. So let's Let's see, what's the best way to do this? Do I want to have a bunch of different graphs? Well, let me at least make one more graph. So this interval will go from 1 to 1.5. F of t is equal to 16t squared. Delta t, which is equal to h. What is the length of this interval? 0.5. 1.5 minus 1.0 if we didn't have the graph, right? That's how we can calculate it. Now we just need the y values. We know that this is 116. But for 1.5, that's going to be a new value. So 1.5. And to calculate it, I just have to take 1.5 and substitute it in for t up there. So I'll give you guys a second to do that. Substitute in 1.5 in for t squared and then multiply by 16. Tell me what you get back. $36? Is that the consensus here? 36? $1.5, 36. Okay, so once again, the change in y divided by h. $36 minus 16, all divided by, in this case, 0.5. 0.5. The length of the interval is 0.5. So take 36 minus 16 and divide that by 0.5. I don't see what we get back. Well, 36 minus 16, that's 20. And then 20 divided by 0.5, 40. 40 feet per second. 40 feet per second. Okay, questions up to this point? Okay, now, what do you think we're going to do? What do you think we're going to do next? We want to get smaller with this interval, smaller, smaller, smaller. So I've been kind of going slow here. We started with an interval length of 1 at 0.5. Let's get really small, okay? Let's say that h is going to be 0.1. 0.1. Okay, so a very, very small step, 0.1. We need to calculate the speed here, and we'll keep doing this and get smaller and smaller and smaller. Let me ask you, if I told you h was 0.5, like in the previous problem, we were starting, remember, up here we have t is equal to 1 way up here. So we're doing this all for t is equal to 1. If h is the length of the interval, and I take t is equal to 1, because that's what the problem is asking for, right? T is equal to 1, and I add the step to it. That's another word for this. It's called a step. If I add that to it, 1 plus 0.5, what does that give me? 1.5. And then I knew, okay, I need to take 1.5, plug it into there, get my y value, and I can calculate that this was 40 feet per second. Without the graph now, if this is 0.1, how am I going to do this? How am I going to complete the problem? Yeah, 1.1. So I'd have to take 1 plus this, and that gives me 1.1. So my T1 is 1. This is where we're starting from all the time. That's what the problem is asking for. But my T2 is 1.1. So what I'm trying to do now is kind of wean you guys off the graph. So let's, T1 is 1, T2 is 1.1. Obviously, that gives a length of an interval of 0.1. But I still need my y1 and my y2. Yeah. Y1 is 16, just like it's been. But what's y2 now? You'd have to take 1.1, and you'd have to substitute it in for t in the original function, 16t squared. So 1.1 raised to the second power times 16. And let's see what that gives us. 19? Times 16. Yeah, 19.36. You get a decimal, right? Yeah, let's take it, since it's small, let's take the whole thing, 19.36. So down the line here, the change in y divided by h, but h is the same as the change in t. 19.36 minus 16. T2 is 1.1. T1 is 1. Of course, we already knew that this was going to be 0.1. We specified that at the beginning, so there's no surprise there. All right, so take 19.36 minus 16 and divide that by 0.1. Let's see what we get back. You should get back 33.6. 33.6. Is that what you guys got back? All right, so the general idea here, just because I know this is kind of a long process, but since this is the first time you're seeing it, I want to make sure that we go through the steps, that I'm as thorough as possible here. And then we can move it along as we do more problems. We start out with a length of 1, then a length of 0.5, then a length of 0.1. We're getting smaller and smaller and smaller. Since we can't do it at exactly t is equal to 1 because that interval is 0, that's fine. We can get really, really, really close to 1 and find that interval, and it should give us a reasonable approximation. That's the general idea here. We're getting really, really, really close to 1 and seeing what happens. All right, so we did this for h is equal to 1, 0.5, 0.1. Where should we go from here? If you want to go even smaller, what would you want to use for h? 0.001? Right? So that's the idea. You keep getting smaller and smaller and smaller. All right, so you've seen me do this a few times. Take it over. Tell me what the speed will be when h is equal to 0.001, and you can use this as your guide, okay? Just make sure you're on the right track. Your T1 should be 1, because that's what the problem asked for. What should your T2 be? 1.00. How many of you think you have it already? Let's take a look. Like I said earlier, T1 is equal to 1, T2 is equal to 1.001. So therefore, the length of this interval is 0.001. The y1, it's going to stay the same. That's just 16. Since I'm very, very close to 1, I'm at 1.001. This is also going to be a number very, very close to 16. You've gotten 16.032016. Now, since this is an intermediate step, that's why I'm taking so many decimals here. Remember, for intermediate steps, you want to take as many decimals as possible, and then at the end, you round it in. Okay, so the change in y divided by the change in t, 16.032016 minus 16 divided by 1 minus, I'm sorry, 1.001 minus 1. And of course, this is going to give us an h value of 0.001. On the top, you end up with 0.032016. All divided by 0.001. And you should have ended up with, see what you end up with, 32 point something. 32.016. All right, so you've kind of seen, some steps here. What does it look like our speed is approaching? What is it getting closer to? 32. Looks like it's getting closer to 32. Closer and closer to 32. And that would be our answer for this problem. It would be 32. In fact, if you were to take an even smaller interval, if you were to take 0.0001, you see that you're getting even closer to 32. So our speed at t is equal to 1 is about approximately 32. Approximately 32. So the idea is they're asking us for the instantaneous speed at t is equal to 1. But that interval is 0. There's no length. So we have to create our own interval. And we could have taken small, instead of starting at h is equal to 1, we could have started right away at 0.5 and gone from there. I wanted you to see how the interval gets smaller and smaller and smaller and smaller. So you're trying to get very, very close to 1. Now in practice, you could probably just automatically start taking values very, very close to 1. That would probably be in practice the best way to approach it. So start at 1.0. Start at 1.0001 and see what you're getting closer and closer. Now I'd like you to do this exact same procedure, but for the second part of the problem, t is equal to 2. Tell me what approximately the speed is as we get to t is equal to 2 seconds. If anybody has any questions on how to start, just walking around. Yeah, it's still you don't have to start like So guys, you pick the length. You pick the length of the interval. But since when I did it, I was trying to show you the idea. So I started out kind of big. You should start relatively small, maybe at 0.1 or 0.001. Okay? That way you can get to the limiting value faster. Right? Once you get this. Okay. You have a question? Go ahead and come back. Don't walk away and go, okay, yeah, you want to ask.
Like,
Yeah, this is because this is the one of interest.
so it's not like 2.001, that's it.
You can maybe start at 2.1 and then go to 2.001 and then it's one.
So you disable to the second power to get Y2.
Yeah, same procedure, same function, same function. And let's do try to do at least 3 iterations. So do this 3 times. So maybe 2.0 and then 2.001 and 2.0001. So you can see how close the values are, okay?
We already know that. We already know that.
A 2.1? For 2, yeah. 2 is 64, right? And then, but then you want to take values kind of close to 2, right? Maybe 2.1, 2.01, 2.001. I just registered. Oh, that's fine. Yeah, I understand. There's a lot of the extended registration stuff. Oh, that's fine. Thank you. It's on black. Everything's on black. Just go over it if you have any questions. Next time we meet, just ask me, or you can email me if you have any questions you have. Awesome, thank you. Right now, just try your best to keep up the way you're doing. The lecture you've been recorded, you're being recorded right now. So when you get home, you can go over, you can review to see what you missed. Yeah, that's gonna be on the video.
Thank you.
I mean, so you started your
Yeah, 2.11 plus.
Oh, 2.1 squared. Okay, and then you multiply by 16. It is minus 16. That's how the. So divided by
Pero,
1. Yeah. Yeah. Minus 16. Minus 16. Where do we start off?
See it?
Where do we start off?
We start off 2.1.
It's 64. Yeah, we got the 16 because it was 116. We're using the 5 and then 2 and 1 is 64. So we're gonna use minus 64.
Divided by 0.01.
I didn't write that.
No, bro. Do you see this? You get this out of this, right?
So we're still using the same function, right?
So it's
Yeah, 16
minus 16.
After the 16.
See, wait.
Yeah, yeah, why two?
Wait.
This is problem. Where's the second part?
Yeah.
We did one of it. That's two.
No.
No, so for T2, post it, and that would make your intervals. Oh, what we Which problem are we doing? We're doing example 2, we're doing the second part. We did the first part together, and I'm giving them a chance to practice the first part.
That's really good.
So this way one equals
T1 is 2.
But this somehow correct.
no, Cody, bro.
So this is your first iteration, right? Yeah, then do it again.
Oh.
Can you switch to the smaller?
So the answer 64.6.
It's getting closer and closer to that value, yeah.
Wait.
Your ID
Yeah. Take another in.
0.006.
minus 3 zeros.
Yeah.
Now, do it for the smaller. So this length is 0.1.
So nomás le haces al otro cero.
Yeah, and that's just
Oh, yeah.
Yep.
Sí, me hace.
Okay, guys. For t is equal to 2, and this is just I'm missing the y-axis here, but I just want to focus on the t-axis right now. So we're at 2, and I told you to pick a small value that's close to 2. Bless you. If you pick, let's see, so if this is 2 and this is 3, let's say you pick this value over here, and let's say that this is 2.1. Okay, if that's 2.1, what's the length of this entire interval? It's going to be very, very small, but it's going to be 0.1. So h is equal to 0.1. So h, and so you always got to refer back to what I told you. H is the length of the interval. The length of the interval. Now I saw several of you doing it for 2 and for 2.1. At 2, you know that the y value is 64. So t1 is equal to 2, y1 is equal to 64. For the y2 value and the t2 values, this is 2.1. y2 is equal to, what is it? 70.56. There weren't any extra decimals at the end there? Was it just 70.56? Okay, I'm just checking. Now the change in y divided by the change in t. This is 64. 70.56 minus 64, all divided by 2.1 minus 2. However, you already know that this is going to be a length of 0.1. 0.1. If you chose a smaller one, that's fine. I mean, we're going to get to the same place. All right, so you take the difference and then you divide by 0.1. What do you end up with? 65.6? Okay, good. And now I want you to do it a couple more times. So let's, here off to the side, let's do another iteration. Let's say h is equal to 0.001. Well, let's do 0.01. Let's go in order. Like that. T1 is equal to 2. Y1 is equal to 64. That doesn't change. It's the same. Why doesn't that change? Why do I keep bringing that down? The T1 and the Y1. That's what the problem was asking for, right? T is equal to 2, so we're trying to get closer and closer to 2. In the book and in other books, you might see this labeled as T0. It's just a labeling issue, that's all. So our T2 would therefore have to be 2.01. And I want those extra zeros in there already. Y2. 64.64? There's no extra decimals there at the end? .64. Let me input it on mine real quick. I think there should be a couple of extra decimals there. 2.01. Yeah, 6416. 6416. All right, now take the difference of the y values and the t values. So change in y, change in t. 64.6416 minus 64 divided by 2.01 minus 2. Of course, this is an interval of 0.01. And what do we end up with here? 64.16. Very good. All right, so we went from 65.6. Oh, and I'm being a little lazy here. There are units here, right? They're feet per second. Feet per second. Because I'm getting so excited during the problem, I just forget about feet per second. Let's do one more iteration, one for 0.001. And I'll do this at the bottom. T1 is equal to 2, Y1 is equal to 64, T2 is equal to 2.001, Y2 is equal to, let's see, when you take 2.001 and you substitute into our function, what do we get back? Do that real quick. You guys get back 64.064016. All right, now it's the same game. You take the change in y divided by the change in t. 64.06416 minus 64, not 16. All divided by 2.001 minus 2. And this length is 0.001. And for this answer, you should get back 64.016 feet per second. All right, so just using 3 iterations, you can kind of see the trend here. We went from 65.6 to 64.16 to 64.016. If you keep going with this, the numbers are going to get closer and closer and closer to 64. Okay, so we're up at approximately 64.
Do you ever use numbers less than 2? Say 1.9999?
You can, yes, absolutely.
Okay,
Yeah, and it would still be valid.
because you're still approaching
You're s-
64, but it's just
From the other side,
from the other side.
yeah, it's absolutely valid, yeah. Yeah, it's a good point that you make there. Yeah, it can be on either side. Okay, so hopefully you have a better idea now of how instantaneous speed works. Instantaneous speed. So it's a little tricky here. And we'll see later on that this concept, I just want to make sure you have it there, but it's going to get a little bit easier. Okay, a little bit easier as we move along.
Did you want us to go to
That's up to you. Just try to make it as clear as possible for me where your work is. The next one, suppose that a ball is dropped. I want you to work on that at home, okay? This will be your let's not use that dirty word homework. This is your practice. But it's the same idea. The only difference is the function is going to be a little bit different because it's in terms of meters. However, I've given you that equation already. What is the equation you're supposed to use? 4.9 t squared. That's the only thing that's going to be different. Okay? 4.9 t squared. Okay, so have you noticed a lot of the examples that we were going over, we're always using t. Of course, it's not always going to be t. It could change to x. And let me go to the definition already, just to show it to you. Okay, so the average rate of change, y is equal to f of x, with respect to x over the interval x1, x2 is defined as this, which is basically what we've been going over. It's just with x now instead of t. And instead of using y2 and y1, they're using f of x2 and f of x1. But it's the same thing, exactly the same thing. Let me show you how they end up from this equation here to this equation. You can see how that's derived. So I promise this one won't take as long as the other ones. Okay, so suppose we have x1, x2 here along the x-axis. This is the y-axis. I have some type of curve, some type of general curve. It doesn't matter what it is. Maybe I should make it a little more parabolic like that. That's better. And this curve continues. At this value here, this is just in general f of x1. This is f of x2. So let this be point P. Point P has a coordinate of x1, comma, f of x1. I need another parenthesis around that. That's point P. And then the point to the right of it, Q, has a coordinate of x2, and then comma, f of x2. And I need to close that parenthesis. So this is your, I mean, it's already there. It's basically numbered for you. If we look at the change in y divided by the change in x, you can pretty much see why it's f of x2 minus f of x1 divided by x2 minus x1. It's just like what we were doing for the average rates of change in the other examples. Bless you.
Thank you. Thank you.
Now this interval down here, I've talked about at length what it's equal to. This is the change in x, but what's that equal to? H. It's the same as h, the length of the interval. The length of the interval. Now the change in x, I have an equation for it, an explicit equation for it there. The change in x is x2 minus x1, right? Okay, so what I'm gonna do is I'm gonna come down here. Instead of writing down the change in x, I'm gonna write down x2 minus x1 is equal to h. Just substitute it. And I'm gonna solve this for x2. I'm gonna add x1 to both sides of the equation. If I add x1 to both sides of this equation, what am I left with? H plus x1. And just so it'll be consistent with the formula, let's put the x1 first, x1 plus h. It's the same thing, right, because addition commutes. So what I'm going to do is I'm going to go back up here to the equation wherever x2 appears. I'm going to replace x2 with this expression x1 plus h. So going downward from here, f of, instead of x2, I'm going to write down x1 plus h minus f of x1, so that stays the way that it is. And then x2, once again, I replace it with x1 plus h, but then minus x1. So the x1s are gone, they cancel out. So the x2, this is where x2 used to be. And I replaced it with its definition, x1 plus h.
So it's just going to be h by itself.
Yeah, it's just going to be h by itself on the bottom. So to simplify this further, we have f of x1 plus h minus f of x1 all divided by h, which is the definition that they give us. And of course, h cannot be equal to 0. And I've shown you why h can't be 0. You've seen what happens. It's undefined. Any questions over this? It's not really a derivation. I'm just showing you why the definition is the way that it is. Do you guys have any questions here?
That's your rate of change.
Yeah, average rate of change. Average rate of change. So then when I'm looking at instantaneous rate of change, it's pretty much this. But how does this change? Well, what have we observed so far? Like for the other example, when we were looking at t is equal to 2, we were looking at values very, very close to 2, where the interval was very, very small. The h was very, very small. Remember, h, we did it together. H was 0.1. Then h was 0.001, and then 0.00, and we kept going. What do you notice about h? What is it getting closer to as I get smaller and smaller and smaller? So I went from 0.1 to 0.01, 0.001. I'm going towards 0 as h gets closer and closer and closer to 0. We can't actually say h is 0 because if h is 0, then this is undefined. But as h gets closer and closer and closer to 0, I'm getting at that instantaneous speed. Okay. And right now I'm talking, very informally, but we'll formalize it in the coming sections. Instantaneous speed. We'll talk about limits and stuff. Now going back to this graph here, P and Q. I'm going to connect these with a line. This line has a name. See if I can get this line straight. This is called the secant line. And the secant line is the line joining 2 points on a curve. If we were to draw a series of secant lines for the other examples that we did, maybe we should just, this is fine. So the length of this is h. Remember, the idea is to get h smaller and smaller and smaller when we're looking for instantaneous speed. So if my h was half of this and I ended up right here, the secant line would move. And if I made it smaller, the secant line would move again. The secant line would basically move along this curve until it's at this point, as h gets smaller and smaller and smaller. This line that barely touches this point in this curve, that's called the tangent line. The tangent line. But we're going to talk about that more in a moment. But that's how secant lines and tangent lines are kind of connected here. Now this secant line, it is a line. It has the properties of a line, meaning it has a slope. You all are familiar with the concept of slope. Essentially, when we do this, this should look very, very familiar, this equation from college algebra. This is the equation for the slope of a line through 2 points. So calculating this will give us the slope of the secant line. Okay, so let's look at defining the slope of a curve. The slope of a curve. You guys have any questions over anything that I talked about here?
We use that to find the secant line.
The slope of the secant line. Slope of the secant line. Essentially, that's what it is. Okay, so a line L is tangent to a circle at a point P if L passes through P perpendicular to the radius at P. So that's a little wordy. Basically, if you have a line through a point P on a circle, and that line creates a 90-degree angle with the radius, then we say that this line L is tangent. Okay, it's tangent. So first we'll look at it for circles, and then we'll look at it for general curves. For circles, I think it's pretty straightforward. For curves, it's a little trickier. But I kind of alluded to it earlier. So let's see if we can understand it a little bit better. Now for a general curve, something that's you know, something like this, some kind of general polynomial. You start with the secant lines. The secant lines, like what I showed you earlier. And basically, what you're going to do is, so for example, let's see what that is. So this is your curve, okay? And this is your secant line through the two points. And what we're going to do is we investigate what happens as Q approaches P, as Q gets smaller and smaller and smaller towards P, as the distance between them gets smaller, as H gets smaller, basically. And what we'll do is whatever the slope is, once we get here, that's the slope of the curve. That's basically what it boils down to. Now, in the definition up here, they talk about limits. Limit is what the function is approaching, what value we're getting closer and closer to. That's what it means by limit. Now, we'll give you the formal definition of limit in the coming sections, the delta and the epsilon definition. But for right now, it's just sufficient to know that when I say limit, I mean, you know, as we're getting closer and closer to some value. So that number 3, it kind of pretty much summarizes it. If the limit exists, take it to be the slope of the curve at P and define the tangent to the curve at P to be the line through P with this slope. So if the limit does exist, then take it to be the slope of the curve at P. So this would be the slope of the curve at P. And we'll define that to be the tangent line. Now, we're going to look at an example of how to apply this, so it's a little more concrete. Look at example 3. Find the slope of the parabola y is equal to x squared at the point 2, 4, and write an equation for the tangent to the parabola at this point. So it's asking for a couple of things. Now for this problem, we might want to use Mathematica to quickly draw out the graph. So let's bring back Mathematica. I'm going to plot again. In this case, my function is x squared. So I have x to the second power. And in curly braces, I'll have to define my interval. Now we want to investigate the slope at the point 2, 4. So we should have a fairly big interval, I think. Let's go, okay, maybe not too big. Let's just go to 3. Now the variable in this case is x. So I'm going to type x. I'm going to start at 0, and I'm going to go to 3. And once again, to actually get the output, you have to hit shift, hold down shift, and then hit enter. And it'll spit out the graph. Sorry. All right, so we need to copy this over to the notes. I keep doing that. I'm going to keep doing it. It's got to be that paste picture. All right, so find the slope of the parabola y is equal to x squared at the point 2, 4, and write an equation for the tangent to the parabola at this point. So we're at 2, 4 up here. I'd like to specify some type of general interval, okay? What is the length of this interval? What have we been calling it? H. You could also call it, delta x, or the change in x. It's the same thing. Well, I try to draw it so that it's a little more general. Don't look at these numbers right now. Okay. So we're starting at 2. My length is h, but I'm not specifying a number for h. I just want to keep h in general. So this point down here, it would be whatever I'm starting at, which is 2, plus the h value. That's what this point would be in the end. It'd be 2 plus h. You guys follow me there? All right, so that means this point up here and that coordinate has to have an x component and a y component. What would I write down for the x component? Yeah, the x component would be 2 plus h. Yeah, so how would I find the y component of that? Not quite, not quite. It is, I'm looking for the y component, right? I'm looking for the function value. To find function values, you take the x value and you plug it into the function, you get back the y value. What's the function that we're looking at? X squared. So I have to plug in 2 plus h in for x. Yeah, so it'd just be 2 plus h squared. Two plus h to the second power.
Can you explain what you did again?
From how we got from, I got this value over here.
Or, yeah, you got that whole thing.
The whole thing. All right, so h is some interval. It specifies some type of interval. I'm starting at 2 down here. So 2 plus h would put me somewhere over here. We don't have an exact value for it, so we're just doing this, just in our mind. Yeah. And if this is 2 plus h, that gives us an x value of 2 plus h. But to find the y value, I'd have to take this x value and plug it into the function y is equal to x squared. So that gives us back 2 plus h to the second power. Now the average rate of change, we know how to calculate that. It's the change in y divided by, in this case, the change in x, because we're looking at x values now. How would I write out the change in y?
H squared minus 2.
Minus 4. Minus 4. This is my y1. This is my y2. And what about for x? Minus 2. This is my x2. This is my x1. It's a little more abstract since we're leaving h as just a general letter, but the concept is still the same. y2 minus y1 divided by x2 minus x1. Not yet. We have to FOIL it out. 2 plus h to the second power means you have 2 plus h times 2 plus h, and you have to multiply that out. You're off to the side. 2 plus h times 2 plus h All right, so let's do this one together quickly. The first, 4 outside, 2h inside, 2h, and then last, h squared, combine like terms, 4 plus 4h plus h squared. That's the FOILed form of it. FOIL, right? First, outside, inside, last. If you don't see that, if you've forgotten or you've never seen FOIL before, you're just distributing. 2 times 2, 2 times h, and then h times 2, h times h. And you're adding them in between. All right, so I need to come back over here to the problem and substitute that in here. 2 plus h squared will become 4 plus 4h plus h squared. Minus 4, all divided by 2 plus h. Okay, well, before we do that, in the denominator, 2 plus h minus 2, what happens?
H.
Yeah, you're just left with h. The 2's are gone. So to make it easier for ourselves, let's just write down an h right here. Yes?
I just got one question. Why is it the y to 2 plus h to the second power?
Because the function that we're using is y is equal to x to the second power. So if I give you an x value, like 2, how do you find the y value?
Yeah, y. Yeah, yeah,
You see it?
yeah, yeah.
Yeah. All right, now for this numerator, do you see any room for simplification? The 4's are gone. So bye bye 4's. 4h plus h squared divided by h. And in the numerator, we have h's in common. So we can factor out the h. Yeah, all divided by h. H's are gone. Well, that was more like an n, but there you go. The h's are gone. And you're left with 4 plus h. 4 plus h. Okay, so what does this mean? So for some value h, this basically is the slope of the secant line for some specified interval h. Now, the general idea to find the instantaneous speed is you want h to get smaller and smaller and smaller, right? Where do you want h to go to?
Approach 0.
You want it to approach 0. You want it to get close to 0. If h were to get closer and closer and closer to 0 here, what would happen to this expression 4 plus h? So let me write that out actually. As h gets closer to 0, what happens to 4 plus h? It goes to 4. It goes to 4. And that's the slope. That's the slope of the curve at the point. So it approaches 4. When I say it, let me be a little more precise. The slope approaches 4. At the point 2, 4 approaches 4 as h gets smaller and smaller and smaller. Now we're not done with the problem because they did ask for something else. What did they ask for? The equation of what, though? They specified, right? The equation of the tangent line. All right, so that means you'd have to know the slope of the tangent line. So that this actually implies that 4 is the slope of the tangent line. Tangent line at the point 2, 4, of course. at the point 2,4. So you need to see the connection here. The slope of the curve at 2,4 is the same as the slope of the tangent line at 2,4. They coincide. What do I need to write out the equation of a line? What information do I have to have? That's the slope-intercept form, right? But in general, you have to have a slope, right? You got to know the slope of it. And you also have to know what? Kind of. That's half of it. You also got to know the y value, implying you have to know a point on the line. So you have to know the slope, and you have to have a point on the line. Alternatively, you just need 2 points. If you have 2 points on the line, you can write out the equation of the line. But for our purpose, we're going to use the fact that we have the slope, which is 4, and we know a point on the line. What is the point that we know? 2, 4. And let's use the point slope form for this. Man, I went off the rails over here. All right, so let's do the second part where it says write an equation for the tangent line to the parabola at this point. So to do that, we'll use y minus y1 is equal to m times x minus x1. This is called the point slope one. We've already established that our slope m is 4, and the point on the line that we're going to use is 2, 4. We talked about this already. Substitute this information into the point slope form and tell me what the equation of the line is going to be. I'll give you guys a minute to do that. Should be able to do it. This is what you should have ended up with. 4x minus 4. Is that what you ended up with?
Yep.
I hope so. So, are there any questions so far? This concept that we applied for example 3, there are some practice problems at the bottom.
So that's the tangent.
Say it again. That's the equation of the tangent line. Yeah, that's the equation of the tangent line to the point 2,4. That's what that equation represents.
Can you go back up to it, please?
Yeah, real quick though. So example 3, it'll help you with these 3 problems. Okay? I'm going to read example 4 so we can take a look at it. All right, so you've read it by now. This is the graph. What are they asking us to find? The rate, the average rate of change, average growth rate, over what?
Over day 23 to day 45.
Day 23 to 45. So they're specifying an interval here. They're asking us for the average. So you're already well versed in calculating average rate of change. So how should I start this? What should I do to start this? This is my p-axis. This is my t-axis. Yeah, so the points at 23, this is a nice graph already created for us. I have 23, 150. And at 45, I'm right over here, I have 45, 340. Is that enough information to calculate the average rate of change?
Yes.
All I have to do is take the difference, the change in the P, divide that by the change in the T. 340 minus 150, all divided by 45 minus 23. That's the y2 minus y1 divided by x2 minus x1. Although in this case we're using pt. So p2 minus p1 divided by t2 minus p1. Using a calculator, what do we end up with?
Uh,
190 over 22, and we're going to get an approximation here. What is the approximation? 8.6? 8.6. So that's why I scratched this out, because the answer was right down there. 8.6, and this is flies per day. That is the growth rate. All right, so not really anything different from what we've been doing. Okay, but what if I wanted to know the instantaneous rate of change at 23 days? Okay, what if I wanted to know the instantaneous rate of change at 23 days? How could we approach that?
Plugging 23 to T. Substitute 23 to T.
Well, this is predicated on you having an interval. If I specify just 23, there's no interval there, right? Interval 0. So there's a problem we've been over before, right? We have to choose values close to 20, close to 23. But we don't have a function. There's no function for us to work with. So we have to use estimated points on the graph. So let me point you in the right direction here. So let's start off with 40. This point right here. This is about 40 and still 340. And we'll go to 35 And this value is approximately 310. 310? Yeah, 310. So 35 and 310. And then 30 and 265. Now, the reason why I'm giving you these points is I want you to look at the secant lines, the slope of the secant lines. So we have already the slope of the secant line through 23,150 and 45,340. It's 8.6. Okay, so what happens to the secant line when I go from 23,150 through 4340, and then through 35,310? And as the secant line approaches P, you're getting, it's going to look like a tangent line. And it's not going to be exactly the same, but we'll be close. It'll be an approximation. So calculate the slope of the secant lines for these 3 points, and that'll be approximately our slope of the tangent line. So that's something you can practice at home, but let me give you the answer for this one, so that way you can kind of have an idea of what you're doing. Let me grab it real quick. You should end up with it being about approximately 16.4. So it should be about 16.4 flies per day at 23. At the point 23, 150. That's the instantaneous rate of change. So if you can kind of get to that answer. There are, like I said earlier, problems at the end of this for you to practice. They are down here. Average rate of change and slope of a curve at a point. So just extra practice for you guys, extra practice. Let me stop this recording.